Hello everyone. In this video, we are going to talk about the Bellman equation and Q-learning. So we want to look at formulating the reinforcement learning problem. Okay, one of the first formulations, and the common one is called the Bellman equation, and one of the common solutions is called Q-learning. So let's get into that. Before we directly go over them, there are two terminologies, major terminologies and techniques that we need to know before we can open up Bellman equation and Q-learning. One of them is called Epsilon Greedy exploration. What is this? So if you remember in reinforcement learning in general, we need a trade-off between exploration and exploitation, right? Exploitation means taking the policies, the behaviors that we know well, and they yield rewards. They are well known. On the other hand, exploration means looking for new actions, new policies, and discovering new states, okay, which we didn't know, and it's kind of a gamble. They can get you a better behavior, a better policy, or they might not. So you need to fine-tune exploration versus exploitation, because without exploration, you might not find the optimum policy. But if you do too much exploration, you might waste time and at the end of the day, still not getting the optimum policy. So how would you do the trade-off? Okay, there are different ways to practically formulate and apply this trade-off. One of the very common ones is called Epsilon Greedy exploration. What is that? So here you try to do exploration by some probability. What probability? By probability of a number called epsilon, which is between 0 to 1. And you pick this number. So if you pick 0.2, then 20% chance, 20% of the time you do exploration, and with the probability of 1 minus that, which is 80% of the time you do exploitation. Okay, so this is a hyperparameter that you have to pick, and that determines the probability of exploration versus exploitation. So in general, when you want to take an action, this is how you do it. With probability of 1 minus epsilon, you do exploitation. How would you do exploitation? You take the action that will give you the maximum, basically, value function, okay? The one that gives you the maximum long-term return. Okay, that is, of course, obvious. That's the best one that you can do. Or by 20% chance, you just take a random action instead of the one that does the best long-term outcome. Then you just take a random, basically, behavior, a random action. Okay. Now, how would you practically do that? So here you generate a number between 0 to 1. If this number between 0 to 1, which comes from a uniform distribution, is less than this epsilon that you picked, then you explore. If it's more than epsilon, less than 1, then you exploit. Okay, so that is one of the simplest yet most effective techniques for exploration versus exploitation. And when we say greedy, greedy means doing exploitation, okay? Because if a person is greedy, basically, or an algorithm in this case is greedy, it tries to take always the best conservative action, the best action that he knows or she knows or the algorithm knows that it yields a good result instead of trying new things. Okay, so greedy is referring to just going for exploitation, but only with a chance of epsilon, or in this case, 1 minus epsilon. That's one thing. The other thing that is very important to know is called bootstrapping. So what is bootstrapping? Bootstrapping means if you want to estimate something, you use another estimate or update to perform this estimation. And this is different from the Monte Carlo simulation that waits until the very end of the simulations to give you an estimate. So in Monte Carlo, you perform a bunch of simulations, and then at the end of the simulations, you provide an estimate. But in here, you don't wait until the simulation ends. As you go along the simulation, in each step, you use the new estimate and try to update the previous one. Okay, so it's kind of like an online estimate, real-time estimate, as opposed to Monte Carlo that you have to wait and it cannot be super real-time. So in order to clarify this for you, let's go with an example. So let's say you want to estimate the value of number pi. If you watched one of my videos under playlist MATLAB, I showed you how to do a Monte Carlo simulation to calculate pi. And the technique is very simple. So you consider a square with dimension 1 and 1. And inside of that, consider the circle with radius 1. So you create random numbers, okay, with rand command, let's say, for x and for y in range 1 and 0 to 1. And then based on what you created for x and y, either the point falls inside the circle or the point falls between the circle and the square. Now, by counting the number of points inside the circle over the total number of points, so if the total number of points that you created is n and the ones that are inside the circle is m, then 4 times m over n should be an estimate of pi. And the reason is very clear, because the area of the square, right, the square area is simply 1, but the circle area is pi times a radius squared, and radius in this case is 1/2, right? Because the whole side is 1 from this side to this, so radius of this guy is only 1/2, so it's going to be 1/2 squared, so it is going to be pi over 4. So you see, pi over 4 is the area of basically circle over the square, right? Which in this case, I'm approximating that areas by the number of points falling inside them, because if it's a uniform distribution, the number of points falling inside each area is proportional to the area of that shape, correct? Because it's a uniform distribution. So n is proportional to the area of the square, and m is proportional to area of the circle. Okay, so m over n is the same as ca over n, and you see that's pi over 4. So if you multiply by a 4, you get your pi. So in order for this method to work, you need to create a bunch of points. Let's say, I don't know, 10,000, 1 million, whatever number of points. And then for each one of them, you have to check whether x squared plus y squared is less than or equal 1. That's the condition for being inside the circle. Count it, divide by total number, multiply by 4. Now here, if you want to get the estimated value of pi, you have to wait until I generate all of those n numbers, whatever it is, 1 million, 10,000, 1,000. I determine this condition for all of them. I count m, and then at the end, I can give you one single estimate. Okay, that is a Monte Carlo simulation. But if I want to do a bootstrap running average, or we call it the temporal differencing technique, I start with an initial guess and then I keep updating it. Let's say I think my guess is 3. Okay, my initial guess for pi is 3. I know it's between 3 and 4, let's say, so I start at 3. And then as I generate each new sample, whenever I generate it, immediately I update it. How? I say the new estimate of pi is whatever the previous one was plus a learning rate, which could be a small number, times 4 times indicator of whether it's in the circle or not, minus previous one. Now this indicator is similar to the previous one. If the point is inside the circle, the output of this indicator function is 1. If it's between the circle and the square, it is 0. So I multiply that by 4, subtract it from previous pi, and basically that is going to be my update. And you can see that here, this new number on the left, this 4 times indicator, this comes from my new observation. So for my new point, I have to calculate this indicator function multiplied by 4. So this comes from my new observation. This is the previous estimate I had. Subtract them, multiply by a learning rate, and add it to previous one. Okay. So this is what we call a temporal differencing technique. And by subtracting new minus old times a learning rate added to the previous one, it's not like basically the steepest descent algorithms, but kind of similar to that. Here we are not using any basically derivative or anything, but clearly you are trying to move into some direction by some amount, which is called the step size. Okay, so you see here at each sample, you get a new estimate of pi. And to demonstrate that for you, here is a MATLAB code for it. So I use 10,000 numbers and I use a small learning rate. You should use a small one. If you use big ones, you're going to see lots of oscillations. This is my initial estimate. And here I create a loop for both, but in the Bootstrap, all I do is basically in the Bootstrap, what I do is the update. You see exactly this is the update I have. But for the Monte Carlo, I don't update anything. Okay, the Monte Carlo value for pi is done, if you look at it, at the end of the loop. When the loop is ended, the for loop, at the end of it, I calculate a single number. But here, you see, it's a function of the loop counter. So it is going to be a vector instead of a single number, and it updates over time. So let's take a look. Here we go. The actual pi is 3.1415. The Monte Carlo returns 3.1468. And that is this dashed blue line as opposed to the solid red line. And the Bootstrap running average, if you look at it, basically, you can see that it never settles perfectly, but kind of you see as you go further in and you create more samples, it kind of settles at the ultimate value. Okay, so it does have some oscillation, and here was with the small learning rate. If I change my learning rate to bigger numbers, you see wilder oscillations, right? So let me just make it 10 times bigger so you see the effect. There we go. You see, so one of the very important things is about the learning rate. The learning rate should be managed, okay? It should be fine-tuned to small, ideally small numbers. And the better thing to do is as there are more and more data coming, ideally you should damp out your alpha and make it smaller and smaller, which is another thing we're going to see in a second. Okay, so how to change alpha, because if alpha does not go down, there is no guarantee that this bootstrapping can settle down on a number and give you any meaningful result. So just keep that in mind. Okay, now with that, let's go to the Bellman equation. So what is Bellman equation? Bellman equation is trying to basically give you the value for the give you updates for the value function. Remember here when we talked about the value function, which is basically measuring the goodness of a state or state action pair, and it gives you the return function, right? It was the expected value of the return function, if you remember, under the condition that you are starting from a state and following the policy, or you are starting from state, taking action A, following the policy, okay, which you call Q. So the question is, when you want to find the optimum policy, because remember, the goal of reinforcement learning is to find this pi. This pi is the one that maximizes this Q function, right, or the V function. So how would you, first of all, evaluate this V or Q, right? Because you have to have different V's and Q's for different S values or different pairs of S and A, and then you find the best one, the optimum one. So first thing is you have to calculate these Q values or V values, which requires that you run the simulation or the interaction with environment from that point onward until the end of interaction or end of simulation, and calculate all of these individual rewards, put the discount factor behind them, add them together, and then come up with some expected value, which basically meaning you have to run the simulation a bunch of times to get some average or expected value. So the major thing is, how do I get these Q or V values? Okay, how do I do that? Because clearly you see, if I want to do that, as I said, you have to let the simulation run to the end, and you have to do it a bunch of times. Okay, and that's not always practical and easy. Okay, why? Because most of the time when your agent is dealing with the environment, it is getting these rewards one at a time. Okay, so it has to interact with the environment. It has to come from this state to another state, correct? And then what? Once it is in the new state, now it can basically look at the new reward and then more and more move on, calculate these terms one by one and add them together. So the thing is, these numbers do not come all at once. You have to keep moving in the environment and taking actions. So if instead of having this formula here, if I had another version of this for Q or V, where instead of having to simulate all the way to the end, I can update it one at a time. So I basically get a recursive formula, an online update formula for Q and V that will make life easier, because I could update it as I move on in the environment and interact with it. And that is the essence of the Bellman equation. Bellman equation creates a recursive equation for you, where you can, by these recursive equations, you can update the values for either V or Q. That is the essence of Bellman equation. And that is derived from the principles of dynamic programming. Now, dynamic programming is a field of itself, so I don't want to get into that. And just know that this Bellman equation was derived so many years ago, okay? So this equation is nothing new. This was first formulated in 1952, okay, about 73 years ago. That dynamic programming and Bellman equation started, and then it took a lot more years for these Q learning and all the other things come in, and then the basically deep Q learning and so on, which started from 2010 and so on. Okay, but overall, this field has a history of more than 70 years, but exactly calling it reinforcement learning and Q learning and all of those, this took time. So first we're going to see what is Bellman equation, and then we see how we can solve this or simulate this and find those Q values by Q learning, SARSA, actor critic. This video we only focus on Q learning. So what does it say? It says, hey, if you want to update the V value or the Q value, this is how you do it. You need a double summation here, where the first summation is taken over the policy. So your actions are coming from your policy. And then the interior summation is taken over the new state S prime, okay? Where in order for you to go from state S to state S prime, first you need the transition probability to be pre-multiplied by this guy here. Now, what is this here? This is the reward that you get for moving from S to S prime with action A. Okay, so when you moved from S to S prime, the action you took was A, and the reward that you get as a result of that is called R. Right? And then all of the values that you would get after that, so after this S prime, whatever you get to the end of the simulations or the end of interaction with the environment, the rest of that, let me call it VS prime, Before that, I call it Vs. So if I want to relate Vs and Vs prime to each other, what I need to do is all of the future value functions should be discounted by gamma, added to the current reward that I got, and then because I'm going from S to S prime and I need an expected value, if you remember V is actually expected value, I need to multiply all of these by the transition probability, because you always need to know what is the chance that you go from S to S prime. Maybe you don't go from S to S prime, you go from S to something else. So you have to pre-multiply this reward by, of course, the transition probability, and also you have to take it by the policy, okay? Yes, because it's the policy that defines this action that takes you from S to S prime. If the policy gives me another action and that action takes me from S to some other S, like S double prime, then of course I cannot just count it. So I have to multiply both of these probabilities. Now this could be probability or it could be a deterministic function, to basically properly weight them and take the expected value. And this is how you update from Vs and Vs prime. You see now that this current value and the future value are related to each other, and basically this is a recursive formula. So if you start from 0, you go to 1, from S0 you go to S1, from S1 you go to S2, and you can keep repeating that. And for Q is the same thing. Now for Q, since the action is already considered in the Q function, you don't need the policy here. The policy is kind of hidden inside here. So all you need is to get the immediate reward, add it to the future rewards that you have, multiplied by a discount factor, and pre-multiplied by the transition function, take it over all possible states to get the update. And again, you see that the current value of the value function, the current estimate of it and the future estimate of it are again what? Again, related through this recursive equation. Now you might say, well, how did he come up with this? Can you show me the derivation of this? Well, let me show you the derivation very fast. So here we're going to look at V, but if you want, we can also look at Q as well. But since they are essentially the same thing, we just look at V. So V, if you remember the definition of it, is expected value over policy of what? Of gamma to the t times all of the future r's starting from S naught of S, where t goes from 0 to infinity. If you look at this definition, that's exactly this guy here. Okay? That's exactly this one. Right? Why? Because this g that you had in it, this g is exactly that summation. Look at g. If you can see, g is exactly this summation here. Okay, so here we just replace it down, and that is v. Now, what would you do? What you do is you expand this guy. If you expand this for t of 0, what would you get? For t of 0, you get gamma to the 0, which is 1. It's going to be just simply r of 1. And then plus the rest of it, you just write it as is. You just write it as t of 1 to infinity of, again, gamma to the t, and then r of t plus 1. Yes? Now, what is this guy? If I ask you, what is this, what would you say? Inside the expected value. Well, that's exactly this v, but for the next states. Instead of S, it's at S prime or S1. Okay? Yes? Except for one thing. When I start here with t of 1, if you look, when I start with t of 1, the first term is going to be multiplied by a gamma, but here, if you look, the first thing was multiplied by a 1. So the difference between this sigma and this original sigma is here the first term is 1, the next term is gamma, gamma squared. Here the first one is gamma already, and then gamma squared. So what I need is I should basically get a gamma out of this summation and write it like this. And now this guy here is exactly that V, except for you start at S1. So now that guy is that V at S1, where a gamma is factored out of everything to match them. And R1 is here. So I can write V as basically expected value of R1 plus gamma, V at the new S. And this is, as you can see, a recursive formula because the current V value and the future V value are related to each other through gamma, through R1, and through the expected value. Okay? Yes, so that is exactly how you do it. And if you want to rewrite this instead of expected value, you want to write it in terms of basically, because expected value is when you multiply them by their transition probabilities. So here, the fact that you go from S0 to S1, you need your transition probability, and the fact that you are taking expected value over all pi's or over all policies, you have to pre-multiply them by the pi. And here, this S prime here is the same as S1 here. Okay, they are the same thing. So if you don't like it, call these S primes all S1 and S0. So you see that basically relating this V to this double summation is exactly what we derived up here. Look, that's exactly this one here. And you can do a similar thing for the Q. So this is the Bellman equation. Okay, finding a recursive update for the V's or Q's. Now, the goal was what? The goal of reinforcement learning is to find the pi that maximizes this value function. How do you find the maximum, the optimal policy? So here we need to go and look at the optimal value functions and what are the optimality equations, and then how we can basically simulate and solve them. So first thing first is, what is the optimal value function? Because if you plot this V versus pi, okay, of course this V is not just a function of pi, you see it's also a function of states and actions and everything, but clearly it can ideally, of course there are a bunch of local minimas and so on, there is always some pi star and there is a V star that is the maximum point and the value of the function at the maximum. So the value of the value function at its maximum, we call it V star or Q star, which is basically the maximum of all V's under pi as pi is changing. Okay, so V as a function of pi, when pi is changing over all pi's, which V or which Q is maximum, that we call V star or Q star. That's the optimum value function. And then the question is, how do you find that? And the answer is this. Let's take a look. It says, in order to find it, basically, what you need to take, because remember here, when you calculate this V, if I go back, it's a recursive equation, right? It's a recursive one, and you recursively update it. So if you want to get to the maximum, what is the best action that you can take? The best action, if I want to go with this recursive equation and get the maximum, is each time that I'm updating this term here, right? which is basically my future rewards, my current one and the future one. If I take an action that maximizes this, right, that is basically the best thing I can do to get to the maximum V. Because as I said, you go from S to, or S0 to S1 to S2 to S3 and so on, and each one of them is done by some action. So this is like A1, A2 all the way. Yes? And these A's, this is one set of A's. Another one you can go with, for instance, A1 prime and then A2 prime and A3 prime. And then another one with like A1 double prime, A2 double prime, A3 double prime, and so on. And each one of them is for a separate policy. So this is for policy pi, for instance, 0. This is for pi 1. This is for pi 2. So we want to know which one of these policies we should take. It says the policy that is optimal is the one that gives you the maximum momentarily reward, the optimum reward at the moment. So right now, when I want to go from S to S0, S0 to S1, between these three actions that I can take under these three policies, which one do I take? I take out of these three policies, these three pi's or these three actions, the one that give me the maximum return for going from this state to the next one. Okay, so between these A's, I pick the one that gives me the maximum momentarily reward. So maybe that one is, for instance, this A1. When I reach here, then what do I do? Between A2 prime, A2 and A2 double prime, which one do I take? Again, I take the one between these three, let's say, that gives me the best reward for transitioning from S1 to the next S. Okay, so maybe this time, this one is the best one. And then as I keep going, maybe next time this one is giving me the best temporary or current set of rewards. Okay, yes. And then, so now you can say that the best policy is to following pi 1 for the first transition, and then maybe pi 2 and then pi 3. Okay, and then this setup is not really a constant policy, but if you can mix them together and call that optimum policy, the optimum policy is basically coming up with those individual temporary best policies, best local policies. So the optimality condition, if I want to explain it in plain English, is to get the best outcome from state S, take the action that leads you to the best combination of immediate reward and future potential reward. And that is exactly what you can see here. If you want to get the best, you have to have the best combination of immediate reward and what? Best future potential reward, because all of the future ones are in VS prime. They are hidden inside that. And the immediate one is this R. So if you take the action over all actions, the action over A, the action that gives you this maximum basically reward, the maximum value function, that in general over all simulation will also be the best policy, basically. Okay, so you see, if I want to maximize this V, basically I need to maximize this interior term. If I can maximize this interior term, all of those individual actions, collection of them will be the best set of actions or the best policy. Okay, and a similar thing can be said about the Q. If I want to get the maximum Q, all I need is, again, the best combination of current or immediate reward and future rewards under the transition function. And another way to write this with this transition function is to use the expected value and call this R and call that Q prime times gamma. So this formula here is the optimality equation for Bellman. If I want to get it, that's how I get it. Now the question is, how do you get it? Okay, yeah, this is a good formula. It looks so fancy and nice. Yeah, go with the best current combination of current and future. How? Well, the first thing, as I said, that is very critical is to look for these Qs. How do I get these Q values? How do I simulate or get estimates of these Q values so I can search inside of them, right, and find the best policy? Because you see, for the best policy, I need to have estimates of these Qs. And what's the problem for that? Why can I not easily do it? Because this is all of the future rewards. So if I want to get that, I need to run my simulation or interaction with the environment to the very last one, to the end, keep going forever maybe, and keep calculating these Qs, and that is not possible, right? I cannot wait until my simulation is done so I get one estimate of this Q and then run it a ton more times to get an expected value. That's not possible. I need some technique that I can update these Qs on the run instead of waiting for simulation to end. And what's the answer to that? Exactly. We go back to the beginning of the video. The answer to that is this bootstrapping. If I want to update my Qs, I do update on the run, not wait for the simulation to end. I don't do Monte Carlo. And that is exactly the technique for handling Bellman optimality equation, is called Q-learning. So Q-learning is a solution to the Bellman iterative equation or recursive equation by bootstrapping. How? It says, hey, if you want to update the Qs, this is how you do it. The current value of the Q is added to what? Immediate reward plus gamma times what? This here is only the next Q value, not all the way to the end, just the next one. You see, it's only over S prime, doesn't go forever. Between all of the next set of Qs, pick the one that gives you, under all actions, the one that gives you the maximum of them, discount it, add it to the current reward, and then this target, which is the best you can get from this to the next, subtract it from the current Q, multiply it by a learning rate, and add it to the current one to get the updated version. If you look at this, this is exactly like what we did for the pi. Look at what we did for the pi. If you look at the pi, this is the same thing we did, right? A learning rate, the new observation or the new target minus the previous one times a learning rate plus the current one is the new one. Okay, that's exactly the technique of bootstrapping, which in general, we call this technique, we call it, as I said, temporal difference. Okay, now what is temporal difference? If you look at it, if you want to relate it to controls, this is very similar to a proportional controller. Your new value or target value minus current one times a gain plus the new one. If you look at the proportional controller says what? It says Kp times error, and error is the difference between desired and the current, or target and the current, times a gain. So that Kp here plays the same role as alpha for me. Okay, so it is basically acting similar to what we have a P controller in controls, a proportional, that is basically doing the same thing, this temporal differencing. And the important thing for it is this learning rate alpha, which is some number between 0 to 1. How big is that? That is going to play a big role in whether this update will converge to something or it will keep doing crazy oscillations like I showed you for the pi. So setting this alpha, the hyperparameter, is very, very critical, of course, as well as gamma and this R and everything, but alpha is the most important one. By the way, this term here inside the bracket, this one, which is target minus current one, is what we call a temporal error, and we can show it with delta. Okay, so this is the Q-learning technique that is used to basically solve the Bellman iterative equation for optimality. Where does the optimality come from? The optimality is here. You see, I'm looking at the maximum Q. So ideally, this Q should converge to Q star because I'm taking the current best actions at the moment. Now, one important thing about Q-learning is it's model-free. What does model-free mean? Means we do not need to know the reward functions and the transition probabilities. If you look at this update in the Q, there is no transition probability, right? Look at this rule here. There is no this function P of S prime given S. Look here, this function. This function and this one, these are two functions, the reward function and the probability transition probability function. Look at them. I don't have them here. I just have single numbers for them. Okay, you see that one is completely gone, and this one I can replace it with some simple number. I don't need to know an actual function for it. I have to come up with some simple criteria or something, but we'll talk more about this reward function in the future. It's not necessarily always simple, but we don't need to know it. Okay, there are some reinforcement learning techniques that try to model these reward functions. And there is also inverse reinforcement learning, which I'll talk in one of my future videos. There are a lot more terminologies that I need to talk about. But here, I don't need to know any model of anything. Okay? And that is very critical. Now, what are the key properties or advantages of Q-learning? The first one that you learned is it's model-free. So being model-free is the biggest advantage, but it has some more. What are they? One is, we call it off policy. What does off policy mean? Means if this algorithm can converge to the Q star, even if sometimes you move out of your policy. Because when you learn the policy pi, the goal is to follow that all the time to get to the maximum Q. But remember that we also want to do some exploration sometime with some epsilon chance. So the fact that sometimes instead of taking the one that maximizes my Q, I take some random action instead, would that give me a chance for convergence? Because here, I'm not always following the action of maximum Q. Sometimes I take a random action and I move off of the policy. Can I still converge to the maximum Q? The answer is yes. This technique will learn the optimum policy independently of the agent action, so you can sometimes randomly explore and still converge. Now, in order to converge, as I said, we need to fine-tune this alpha. This alpha, it cannot be just any number that we want. It can oscillate big time, because if you remember in controls, the P controller, one of the major things in a P controller was oscillation. That's why we added the D term. Okay, but here adding a D term is not easy. It needs derivatives of this, which we don't have. So if we want to go with this kind of proportional thing or temporal differencing, we need to keep this KP under control and fine tune it. How? One of the things that kind of guarantees a convergence for Q is called the Robbins-Monroe conditions. The Robbins-Monroe condition says your learning rate should be decaying. What does decaying means? Means the value of it should converge to 0 as t goes to infinity. Okay? It should get smaller and smaller as you get closer and closer. As this Q is converging to Q star, your alpha should go down, so this update term gets smaller and smaller. And you see, it does make sense. So what does this condition say? It says sum of the alphas from 0 to for all time points or all simulations could be infinity, but sum of the square of them should not be infinity, should be finite. Okay, yes? So for instance, if you pick alpha t to be 1 over t, which I mentioned over here, although summation of 1 over t for t cannot be 0, but starting from 1 to infinity, this converges to infinity. You know, this guy is not a finite sum. Okay, you know, some of this will go to infinity, but some of this guy, the square of that, this is going to be, if you go from t of 1 to infinity, this is not going to go to infinity. This guy, basically, if you look it up, it converges to pi squared over 6, or 1.64, or 65. Okay, so if I pick my updates, learning rates to something that decays over time like that, okay, then that follows this Robbins-Monroe conditions, and that is kind of guaranteeing that my Q does converge to Q star. Okay, so that is another thing. Then clearly, when we want to, another thing about this is when we update the Qs, we use the bootstrapping that I mentioned for you. We never use actual returns, so we don't need to wait forever until the Monte Carlo simulation brings all of the future returns, and then we calculate them. We update as we go, and then we really do not need to have all of the state action pairs explicitly, which for many problems is impossible. We can learn from the experience and single interactions with the environment. Okay, and as I mentioned, the bootstrapping is shown here, right? In your Q-learning, we are updating all of our future ones by only this current single one and the maximum of them over action. Good. So, although bootstrapping is efficient and makes us have real-time updates to the queue, but remember one thing, that it can causes bias and instability. Okay? It can, if alpha is not properly tuned, and even if alpha is good, still it will converge. It doesn't mean it converges to the perfect Q. It might converge to the Q plus some bias. Okay? And the other thing is, if we try to do function approximation of what? Approximation of transition probabilities or the reward functions, like we'll see later in deep Q learning, then it will have problems over there as well. So if we want to now, we just seen the overall, this Q value and everything, the Q learning, but we never seen it in a real example. Because if you want to see something and learn it, you have to touch it. You have to look at some numerical numbers. So here I want to give you some numerical solution of a navigation problem, right, with Q learning. And we're going to go from there. So what do we want to do? Let's say I only have a grid of 4 by 4. I want to go from this position 1, 1 to the position 4, 4, start and goal. And I have 2 obstacles in position 2, 2, and 3, 3. So my goal is to find the best kind of motion to go from start to goal without hitting into these walls. Okay? So it's a simple grid nav, and you can extend it, of course, to any size that you want. So this is a simple, basically, problem. So how do we do it? Here, we don't have the Q values to search for and to find the best policy. So the first thing is we have to create our Q values, okay? If we can find these Qs and we can update them until they converge, then we can look into all of these Qs and find the best policy. So first thing is, how do we form these Qs and help them converge? Well, of course, in order for them to converge, we have to follow this bootstrapping. But since this is a recursive equation, the first question is, how do you start the Qs? You have to start them at the beginning, right? The answer is you can start them arbitrarily. You don't need to know the Qs, initial Qs at all. So you completely start them arbitrarily. Good? Then what? Then, of course, we have to follow this rule, as I said. Now, how do we do it exactly? So at each step, if we are in state S, at each, and state here, as you'll see, corresponds to one of the cells in this grid. So in this case, we actually have 16 states. Okay? So I have 16 states because I have 16 possible positions for my current location of the navigator to be. You can take some actions in each state. In this case, the only actions you can take are to go left, right, up, and down. That's all you can take, right? So here you only have 4 actions, a finite number of actions, 4 actions. Okay? Now, how would you pick your action between these 4? Not only you have to pick these 4 based on a policy, you also need to explore as well. So you pick these actions either based on your policy or in general, as I said, using Epsilon Greedy. So you create a random number, whether it's less than epsilon or bigger than epsilon. You try to follow the action that gives you the maximum reward for the next transition, or you just pick one of them randomly. Okay? Once you pick that action, you end up to a new state. Once you end up in a new state, right? So here, for instance, I'm right here. I create a number, do Epsilon Greedy, and this Epsilon Greedy says, hey, if you move in this direction, you might get the maximum reward, or if you do in this direction, you get the maximum reward, okay? So that is my between all possible motions I have, because here you cannot really move to the left and top. These are dead for me. All I can do is move to the right or go down. Now between these two, which one will give me the maximum reward? Let's say moving to the right is giving me the maximum reward, okay? So this is with 80% of chances I pick this, which is my best action, but also 20% chance I pick one of the other ones that are available. Now, in this case, these 2 are not available. So with 20% chance, I can also pick to go down. So I take an action, and based on that action, now I end up in a new state. So 80% I end up here, 20% I end up here. And each one of them will give me some reward and some new state, as we said. Okay, so each one of them comes with a reward and a new state. Now that I have R and S prime, I go back to the Q learning equation and I update. Look, I have my previous Q. I ended up in S prime. Now that I'm in S prime, I can look at all of the actions in S prime and find the one that gives me the maximum one from S prime. I discounted it. I added to my current reward, multiply by a learning rate, add it to my current Q value, and get the updated one. And I keep doing that, okay? As I go from S to S prime to another one, and another one. And the goal is you start in S and ideally end up in goal in each one of those episodes, okay? And so you update your Q And hopefully with proper selection of alpha, your Q table kind of converges to something. Now remember, you have to repeat this for a bunch of different episodes. The more episodes you use, the better policy you will find. Because in here, it's very easy. You either have this option or this one. But if the problem has so many dimensions, so many states, so many actions, with one episode going from start to goal, there is almost zero chance that that first round you found your best policy. You have to repeat this and kind of take the average expected value so you can get to the optimum policy. Okay? So here, let me run my code for you first, see what you will get. So here is the code. You see the grid is 4 by 4. I have 4 actions where 1 is up, 2 is down, 3 is left, 4 is right. My alpha is 0.1, gamma is 0.9, 20% epsilon greedy, and I run my simulation 1,000 times. And these are my actions coded as 2 numbers. Goal state is here, start is 1, 1. The obstacles are in 2, 2, and 3, 3. You also need to come up with some rewards here. So I say if you ended up in the goal position, I'll give you 10 points. Per extra step that you take per step, -1. So the one that gets to the goal the fastest, that is going to be the best one, the shortest path. And if you hit any of the obstacle, I take 5 points off from you. So remember, going back to here, we said that we take some action. And this action could be the action that looks the best or some random one. So would I end up each time I start from start, would I exactly in each one of my simulations, I end up at the goal? No. Sometimes I might come here and I end up here and never move. Sometimes I might end up here. Sometimes I might end up here. Sometimes I might hit a wall, sometimes I might not hit the wall, but I take a longer path, right? So there are so many different scenarios that can happen, right? So one time I can go like this. Another time I can go like this. One time I can come like this, boom, to the wall, right? One time I can go like this. So there are all sorts of scenarios. And in some of them, I will get to the goal. In some of them, I will not. In some, I will hit the walls. And some, I will not. So each one of them will get a different total summation. Because I gave it some good reward for ending at the goal. If you get in the goal, I give you 10 points. If you hit the wall, I penalize you. The more steps you take, the more I penalize you. So hopefully out of all those different path that you have taken by following either the best policy or random actions, you can find now your Q values. Okay, by so many simulations, you get to different Q values. So here, you see each time I start all of my Qs at 0 for each one of those episodes, and then I start simulating. Now, here is the epsilon greedy. You see, I create a random number. If the random is less than epsilon, I take a random action. Otherwise, I take the one that has the maximum outcome, the maximum current reward. And then I take an action from the state to end up in the new state. And then you see that here is checking the image bounds. Okay, so if I hit the obstacles, I add the reward obstacle. If I basically get out of the boundaries, I also add a reward obstacle. Okay, so it's not just hitting those walls. If you try to get out of the grid size, I also take 5 points off. If you get to the goal, I add 10 points. Any step, I take 1 point off. And finally, once this is my temporal update, okay, and Q is converged. So if I run this, look here, These are the queues over the more simulations I do. You see they start to kind of, their shades of gray, which corresponds to a number, right? They are starting to kind of converge. As I said, the more episodes means I have tried all different combinations. And the darker the numbers are means they have higher Q values. So what do I have here? I have 16 rows. Each row corresponds to one of the cells in the grid, where I go row by row. So what does it mean? It means row 1 is cell 1, 1. 2 is 1, 2, 3 is 1, 3, 4 is 1, 4, 5 is row 2, column 1, 6 is row 2, column 2, and so on. So I scan those grid cells row by row, and I call them state 1 to state 16, right? So 1, 2, 3, 4, 5, 6, 7, 8, all the way to 16. This is how I basically call my states. Also, remember that this is how I call my actions. So basically, my actions are also shown. That 1 means up, 2 down, 3 left, 4 to the right. So this is what my queue converts to, my queue table, after 1,000 iterations, 1,000 episodes, 1,000 trials. Now what? Now how can I, from this table, I can say what is the best kind of motion, the best policy? Well, here I go in each state and I look at all 4 actions. Which one of them has the biggest combined return, Q? Here I see it's this guy. That's the darkest. And action 2 means what? Means going down. I go to state number 2. Action 4, this column is the darkest, and column means go to the right. So in state 1, it's 2, which means going down. In state 2, it's going to the right. And look here. This is what you have. Now, this is a different table than the one I converged to. So here, this is my final queue instead of that one. Because I can also print my queues, right? And that's what I do in this code. Look, I print the queues. Good. So now, if I look back at the queue at each state, so this is a state 1, I look at the 4 actions. Which action is the highest? Here. Action 4, which is going to the right. So I say here, you should go to the right. State 2, which one? Again, action 4, which is going to the right. State 3, which one? Here, look. Action 2. Action 2 means going down. 4, going down. 5, going down. 6 has no meaning. This has no meaning because this is an obstacle. Basically, this is a wall. So really, we can just ignore that. 7 is going down to the right. 8 is down. 9 and 10 is down. 11 again is a wall, so I ignore it. 12 is going down. 13, 14, 15, all going to the right. And extend 16, which again should not have really anything. If you look at all of the rewards of that are 0. Why? Because once you're at the goal, you're done. No action will give you any more rewards, so all of your estimated future rewards and return should be 0. And that is an indication that your queue table actually converged, is that for the goal row, if each row is a state, for that row, ideally your queues should all have converged to 0. Okay? That is a good indication that it is kind of converging. Right? You see that? Okay? So, and based on that, as I said, you can read your best policies, best actions. So once the table has converged, the final policy at each state is the one action with the maximum Q. So here, with this table, I found my best actions at each location. Good. These are the best actions. Now, how do I call it a policy here? Because policy here is, if you remember, is a function of A given S. So if I say these are my best actions at each location, now how do I create a policy out of that? I want to, let's say, create a deterministic function. In this case, it has to be a table lookup or a basically multi-criteria function. So what I can say is this. If your state is 1, 2, 7, correct? And then 11, 12, or 12, 13, 13, 14, and 15, right? So if S equals 1, 2, 7, 13, 14, and 15, then your action should be moving to the right. And moving to the right, if you remember, was action 4. So A equals 4. Otherwise, it was moving down, which was 2. And if it is actually 6 and 11, and 16, you don't need to define anything. None. Okay, you don't need to take any action because action is not defined for the goal or for obstacles. So you can make it a multi-criteria function like this or a lookup table, right? Which is exactly per each one of the states, you have a corresponding action, right? So 1 is 4, 2 is 4, all the way, let's say here, for instance, 15 is 2. Right? So any of them could be basically a policy for you. Now remember that when your system is continuous and you have infinitely many states and lots of different actions, maybe infinitely many, creating a table or multi-criteria, especially a table, is impossible. So when you're dealing with continuous problem, this approach, the way it is not easily possible. Creating a Q table, which has as many rows as the number of states and as many columns as the number of actions, is not always a simple thing to do or impossible. So for more complicated reinforcement learning problems, we have to come up with different strategies and different solutions, and this simple Q learning will not work. And that is exactly our next thing we want to discuss. So first, we discussed in the past that can the Q learning results oscillate and not converge? You see that yes, if the learning rate isn't high, it cannot. But that's not the only reason that the result can oscillate, the Q table. The other thing is your system is not stationary or stochastic. Like what? For instance, if here this obstacle is moving, this obstacle in home 6 sometimes moves down to this other home, okay? If your environment is not static, then your Q table cannot converge. The other thing is, remember, exploration will create some randomness, and bootstrapping is not waiting until the end of simulation, just updating as we go. These are all creating some stuff for us, which can lead to oscillation in the Q values, slow or no convergence, and bias. Okay, keep that in mind. But these are not the only limitations of Q learning. So let's talk about other things. One that I just mentioned is state action space explosion. When the environment is bigger, you have more states, more actions, the Q table becomes impractically large. There is no way you can form the Q table. That's one. Two, the dilemma of exploration versus exploitation. The thing is, implementing the Epsilon Greedy is very simple. We see how we can easily do it, but it might not always give us the optimal solution and might converge to suboptimal solutions if it's not adequate enough. In other words, if epsilon is very small. The biggest thing also, in addition to explosion in this method, I would say, is sensitivity to hyperparameters. Alpha, gamma, and epsilon, especially alpha and epsilon. If they are not properly tuned, you can easily see bad results or poor convergence. Okay? And the other thing is, we call it offline unawareness. What is that? Remember, Q-learning does not learn a model of the environment, right? It doesn't need it. It doesn't learn it. Okay? So if you want to do some planning for the future, if you want to do a better job with defining the reward function, that might not be possible. There are other reinforcement learning algorithms that try to learn the reward function and also the transition models as they go. Okay, but Q-learning does not need any of that. It's like one of the simplest, the most basic solutions to the reinforcement learning for simple problems. Now, where would you see Q-learning in real life? Although it's very simple and limited, it has been successfully applied to many problems. Like what? Like grid navigation and path planning that I just showed you. For different games like tic-tac-toe and simple games like Simple Pac-Man, it has been used. For autonomous driving and control in discrete setting, path following, lane keeping, it has been used. For inventory management, for network packet routing, okay, in communication networks and in industrial systems, like for instance, a scheduling elevator or machine operation optimization or something. Okay, so it has been used, although very simple, but it has been used, and the goal is in future videos, I'll show you more advanced techniques of reinforcement learning. So thank you so much for your attention. I'll see you in the next video.